All right. So, OBS crashed, and I had to restart the computer, and so anyway, I was just starting to talk about lifetimes. I'm not sure how much got recorded of the previous little bit, but I'll just start over again. Um, so we left off at lifetimes. It's been a while since I've talked. It's been, Christmas and that sort of thing. Anyway, so we're just looking at lifetimes, and I was speculating how lifetime might be the similar concept to scope. And then they use the word scope up here, right there. Scopes are often referred together, but they are not the same. And then I said, cool, here's an example. So the example is going to show me what they mean by the difference between a lifetime and a scope. And then I look at their example, and they label this a lifetime, and then they label this a lifetime, even though in the description they seem to imply that the inner lifetimes are actually scopes, because it says, as a result, the borrow is valid as long as it ends before the lender is destroyed. However, the scope of the borrow is determined by where the reference is used. So there's a reference being used. Sorry. Yeah, but borrow one lifetime ends. See, it's lifetime and lifetime, or ends. Lifetime starts, ends. So I think they meant scope based on the word here, but that's not what they said. And in fact, it says, in the following example, we will see how lifetimes relate to scopes. And then they use the word lifetime for everything here. There's the word scope does not appear in their example. Lovely. Lovely, lovely, lovely. Anyway. Okay, let's move on. Explicit annotation. A borrow checker uses explicit lifetime, here we go, lifetime annotations to determine how long references should be valid. In cases where lifetimes are not specified or elided. Elided. That's an awesome word. Elision implicitly annotates lifetimes, and so is different. Okay. Rust requires explicit annotations to determine what the lifetime or reference should be. The syntax for explicitly annotating a lifetime uses an apostrophe character as follows. Apostrophe A. Oh, that's what that apostrophe was. So when we were doing string, string apostrophe A, so it was actually specifying a lifetime. Say, okay, this should last for whatever. Using lifetimes requires generics. Additionally, this lifetime syntax indicates the lifetime foo may not exceed that of A. Okay. In cases with multiple lifetimes, the syntax is similar. In this case, the lifetime of foo cannot exceed either that or A or B, or prime A, prime B, if we want it. See the following example for explicit lifetime annotation in use. Okay. So, which have lifetimes A and B. These two lifetimes, both at least as long as function print-refs. Okay. Prime A, prime B. So this doesn't feel like string. Function which takes no arguments was a lifetime parameter of A. So when does this become real? So let 49 is 49. Borrows both variables are passed to the function. Print-refs 49. Any input which is borrowed must outlive the borrower. In other words, the lifetime of 4 and 9 must be longer than that of print-refs. Failed borrow contains no references to force A to be longer than the lifetime, but A is longer. This lifetime is never constrained. It defaults to static. All right. I kind of get the general idea. We have this. We want to be able to explicitly say how long should this variable last. And you can imply it, but you can also say it explicitly. Error. X does not live long enough. to use lifetime A as an explicit type annotation inside a function will fail because the lifetime of X is shorter than that of Y. A short lifetime cannot be coerced into a longer one. Let Y okay. But we never use Y. So why would Y have a longer lifetime than X? Because they both end like right here. Unless the implication is that if you declare something, you expect it to be a lifetime just slightly longer? Or is it because we don't use X ever again? Yeah, I don't really... That's not being really clear. Okay. Alright, well, hopefully we'll get a better explanation, but I'm a little fuzzy on... I get the general idea, but the details, not so much. Alright, let's move on. Let's see what happens. Ignoring elision, function signatures with lifetimes have a few constraints. Any reference must be an annotated lifetime. Any reference being returned must have the same lifetime as the input or be static. That static seems like a safe one. Additionally, note that any returning references without input is banned if it would result in returning references to invalid data. Okay. One input reference with lifetimes A must live at least as long as the function. Print 1, A, you get an X, okay. And so that's fine, but mutable references are possible with lifetimes as well. Mutable 32, I32, okay. Multiple elements with different lifetimes. In this case, it would be fine for both have the same lifetime, but more complex cases, different lifetimes. We did that already. Returning references that have been passed is acceptable, but the correct lifetime must be returned. So the A lifetime for X, because X has the A lifetime. Okay. Invalid output A, string A, blah, blah. The above is invalid. A must live longer than the function. Where is invalid output? Invalid output doesn't appear here anywhere. A must live longer than the function. Hence, here, string from foo would create a string followed by a reference. Then the data is dropped by exiting the scope, leaving a reference to the invalid data to be returned. And the data is dropped upon exiting the scope, leaving the data is dropped upon exiting the scope, leaving a reference to invalid. Oh, okay. Because this is a reference to a string. We can't return a reference to a string that was created down here at this level because it'll be dropped. We've seen that before, that whole business of just read it and do nothing with it and then it's gone. So we're taking advantage of that again, where we're but before we were passing in a reference or passing in a reference to something, it was using it, it was borrowing it, and then that's it. And because it borrowed it, it owned it. When it went out of scope, it threw it away. So this is kind of doing all of that inside. It's throwing it away. Man, this is weird. All right, let me play around with this. Let's make a copy of this and see if we can understand some of this stuff here. Because honestly, I do not. File, close folder, terminal, new terminal. What's this? Live share audio is deprecated. Oh, well, gee, that's too bad. cdc / rust. Okay, and we're going to say this is the right directory. So we're going to say lifetime. Cargo new lifetimes. Okay, change tracing lifetimes. Okay, let's go open folder, Rust lifetimes, that one, select folder. Here we go, we've got main, Control A to select all, paste, there we go. Okay, so let's just save this and run it once just to make sure that it actually runs. Run. What does it do? Print 1 is 7, print multi 7, 9, print 1 is 7, print 1 is 4, x is 4. Okay. All right, let's uncomment this line. See what it says. Okay. Let's run that. Oh, here we go. Okay, we got an error. So that's what that looks like. Cannot return reference to temporary value. So that actually makes more sense than their long-winded explanation. We created a temporary variable and we tried to return a reference to it. Yeah, cannot return reference to temporary value. Makes perfect sense. So, duh. I don't know, that was like really confusing, their explanation. But this error message, oh, and look, temporary value created here returns a reference to data owned by the current function. Yeah, cool. So what if you did want to create something in here and have it be returned? Could you get rid of the ampersand and just say, return me a string? Would that work? What's this? This is never used. Okay, but it doesn't complain. So if I said print line exclamation mark, is this a string? Yeah, invalid input. Output. Oh, what's this? Format argument must be a string literal. Oh, okay. Really? You has to be like that? You can't just take any old string? All right, cool. So let's run that again. Foo. Foo. Yeah, so that worked. Okay, so I can create a string and return, because I think, remember we had that whole thing, some things are on the stack and some things are on the heap. I believe when we do the string : from, you can create a string from a string literal. Does it say? Oh yeah, this buffer is always stored on the heap. Okay, so yeah, so we've got this string that we've created on the heap, and now we can return it because it's on the heap. We've got a pointer to the thing in the heap, and cool, here you go. Here's a string. So we can't. But the other one, I think, what we were trying to return a reference to it. Well, I mean, it's still creating the thing on this. So it's still creating the thing on the heap. It's just that with the ampersand, we were saying we'd like to return a reference to this string. or maybe a reference to this reference to a string. But here we're actually just returning the string, or a pointer to the string. So I'm not sure why you can't go pointer to string, unless I think because I'm borrowing. The ampersand is borrow, not. I keep doing the C thing, and going, oh, that's an address of. No, it's a borrow. We're borrowing. Right. But the place we're borrowing it from no longer exists. That's the problem, I'm guessing, here, right? So we could borrow, but the lifetime of the place and that's what it said. Yeah. We can't, the place we're borrowing from needs to exist when we're done borrowing. So with the ampersand, we were borrowing. With this thing, we're not. So, cool. Okay, got it. Got it. That makes sense. So, let's put... Oh, no. We want to do... Anyway, it doesn't matter. I was going to put it back and leave it in the comments, but too late. Oh, I know what I could do. I can go back to here and grab this line. Copy. And then paste. Now, the above is invalid. A must live longer than the function. Yeah, there we go. Although I'm not sure why I have an A thing here. Now, what if I don't have the A thing here? Is that going to be okay? Run. Yeah, so why do I have the A thing there? I don't know. I don't know how useful it is. Because see, this print multi, we're saying, yeah, we have lifetimes, but what are you trying to tell me? Because we're annotating these things, but we're not really... I mean, we're not... It doesn't feel to me like we're using the annotations. Because I don't think it makes a whole lot of difference whether we annotate the things or not. Because I think there's some default annotations that are occurring. And we just happen to kind of tag along with the default annotations, where it just kind of follows. But I'm sure at some point we're going to bump into some place where we actually need to explicitly annotate because the default lifetime is not sufficient. But I think we need to get way more complicated before that is something we need to worry about. All right. So that's cool. Move on. Methods. Methods are annotated similar to functions. Function. So methods are functions, but So right, because methods are attached to objects, right? Methods are attached to objects. Functions are just the things that float there, although they're both notated by the fn. Okay, cool. Structs, annotation of lifetimes, and structs are also similar to functions. Borrowed A. We also have the structure. Okay. Alright. Cool. I don't know. I'm just going to skip over this. Not try to understand too much about it. Traits. Annotation of lifetimes and trait methods basically are similar to functions. Note that impl may have annotation of lifetimes too. Impl A. Okay. Sure. All this stuff is just stuff you're accumulating in memory here, with the idea that we're going to eventually, this is going to pop out and we're going to go, oh, I remember something about that. We need to go look that up again. Bounds, just like generic types can be bounded, lifetimes themselves generic use bounds as well. But the colon character is a slightly different meaning here, but plus is the same. Note how the following read. T colon prime A colon all references in T must outlive lifetime A. Colon T colon trait plus prime A. So this is not colon all. This is like colon separator. So in T prime A, all references of must outlive lifetime A. Okay. T trait plus prime A, type T must implement trait, and all references in T must outlive A. Okay. Sure. Where did you use that syntax? Not there. Not there. Not there. So this plus doesn't actually, it's not, they didn't really mean plus, I'm guessing. It's like a, yeah. Okay. Yeah, it's ref A prime T colon A. Oh, there's the T colon A. There's the T colon A. And then, then there's just T. And then there's A prime A. Oh, here it is. T. Debug plus A. Oh my goodness. That's because where that's gonna hurt my head. Okay. Okay. Yeah, bounds was already something I was saying, well, maybe I don't need to worry about that so much. And then we're going to throw this syntax on top of bounds, and it's going to be double I don't really care. Or at least I don't care for now. Wow. All right. Coercion. Longer lifetime can be coerced into a shorter one so that it works inside a scope it normally wouldn't work in. This comes in the form of inferring coercion by the Rust compiler and also the form of declaring lifetime difference. Oh, now I'm hurting. I'm really, really hurting here. Never mind. We won't even bother. Static. Okay, Rust has a few reserved lifetime names. One of those is static. You might encounter it in two situations. The string, yeah, that's the one we were saying, the prime static. And static is part of a trait bound, where T colon prime static. Both are related but subtly different, and this is a common source of confusion when learning Rust. Damn straight. Only one? The only common source? Okay, reference lifetime. That's a reference lifetime. Static, prime static, indicates that the data pointed to by the reference lives for the entire lifetime of the running program. It can still be coerced into a shorter lifetime. Yeah, because we have that coercion thing happening, which we ignored. Two ways to make a variable with static lifetime. Both are stored in read-only memory of the binary. Oh, okay. That's cool. So not in the heap, not in the stack, but in your code. Make a constant with the static declaration. Make a string literal which has type ampersand quote static or prime static. Sure. Okay. So make a string literal and print it. Let static string I'm a read-only string. When static string goes out of scope, the reference can only be used, but the data remains in the binary. Okay, that makes sense. It's kind of a C compiler behavior. any strings you declare directly in your code become embedded in the code. Okay. But where's the lifetime thing? Oh, here. Make a constant with static lifetime. Coerce static. Num. At lifetime num equal 9. Okay, and then we need to coerce that into a shorter lifetime. Num stays accessible. Sure, because num is static. Why wouldn't be? Oh, okay. All right. So why exactly would I do this? Oh, I guess because I want it to go out of scope. I want this coerce static to go out of scope. Because I have this thing, 18, and I say, okay, this constant, I want it to live across the entire application. But then I have a particular use of coerce num to lifetime of lifetime num. Lifetime num. Coerce static. So does coerce static contain, all right, let me run this. 9 or does it contain 18? So num is 18. And this thing is going to return. Oh, so are we just using the lifetime of lifetime none? Or are we actually, oh, but it's well, we're not using it though. Okay, so if we run this, I'm guessing it should be 18. 18 stays, yeah, coerce static 18. 18 stays accessible. So this thing here, that thing is, we're passing in a variable, but we're only passing it in because we want to know its scope. That's interesting. Here's a variable. Don't look at its contents, but please pay attention to its scope because we want to use that. Wow. That's an interesting thing. Okay. Trait bound. It's a trait bound. It means the type does not contain any non-static references. The receiver can hold on to the type for as long as we want. Never become invalid until they drop it. It is important to understand this means that any owned data always passes a prime static lifetime bound, but a reference. Okay, what's going on here? I is owned and contains no references, thus it is static. Thus it's static. Let I equals 5. Print it I. Oops. Ampersand I, the borrow of I, only has a lifetime defined by the scope of main, so it's not static. So, alright. What's going to happen here? The compiler will tell you, oh, okay. I does not live long enough, ampersand I. Borrowed value does not live long enough. The argument requires that I is borrowed for static. I dropped here while it's still borrowed. Okay, so again, we tried to force something that we borrowed to have a longer lifetime than it actually has, and then the compiler complains. All right, that's fair enough. That's fair enough. If we can't make things last, especially since this is on the stack. Because if we were able to do that, it would probably have to copy it to the heap to be able to get away with this. But then we're going to explicitly copy it to the heap or create a heap version of it. if we want that to happen. We don't want this thing to do that on our behalf, because I think the point of Rust is we want to be in control of what's in memory. So we want to have to explicitly say, yes, I have this I, and I would like it to last longer than this method, or this function, so let me put it into the heap. I think that's what's going on here. All right, elision. Some lifetime patterns are overwhelmingly common, and so the borrow checker will allow you to omit them to save typing and improve readability. Yes. These patterns are common. The following code shows a few examples. For more comprehensive description, see in the book. Oh yeah, we're gonna have to go visit the book. Simulated pass, annotated pass, have identical signatures because lifetime is okay, whatever. Okay, so yeah, annotated, we have that. This thing is implied, which is what I was saying before, is like we don't really need this, right? Because they both behave the same way, and we've been using, without explicitly saying the lifetime, we've been taking advantage of its, its lifetime is this, without actually saying it. So, that's cool. But it's nice to know that we can say it if we need to say it. Right. Moving on. Now, we're at 16. Traits. All right. So before we go any further here, we got 16 through 24. We've got traits, macro rules, error handling, standard library, testing, unsafe operations, compatibility, meta, whatever. Okay. So at this point in the journey, this is where, I always feel like projects have 3 sections to them. The first section is when you're naive and you go, I got this. This looks pretty easy. I can figure this out. And then the second section where you go, oh my God, I don't understand anything, and I'm never going to be able to figure this out, and I will never deliver whatever it is on time. Then you have the third section, if you get that far, where you go, oh, it wasn't so bad. There was some rough parts, but I've figured it all out. We're deep into part 2 here, right? I mean, we're looking at this list of things and we're going, we've tried to absorb all of this stuff here in this like just layer upon layer of confusing syntax and stuff that I'm kind of going, let's not pay too much attention to that right now. But we I want to wander through the rest of this, but what has to happen before, the next step after this is to actually start writing some code, because I've walked through all of this. I've read all of this stuff. I've kind of tried to form a mental model of what's going on here. And then I'm going to start writing code. And when you start writing code like a blank page and you go, okay, now I want to do something, then you realize how much you really don't know or didn't retain from all of the stuff. But that's okay, because I've got like all these projects and I can go back and I can look at the different projects and like, how did I do this and how did I do that? And then I get stuck and I go, well, I don't know how to do X. And that's where Stack Overflow comes in, and maybe the book, which it just referred to here. So that's kind of the process, right? Is that you don't just absorb all this nonsense and kind of go, here, beautiful code. You kind of work your way through it, and so you start with something simple, but we actually have to write some code. We have to, like, copying and pasting from their code is cool, but honestly, and I've tried to kind of do some things to modify their code, and sometimes I bumped into like brick walls and going, I don't know what I'm doing anymore. Hopefully that's less going to happen less and less over time, but it's never really going to go away, honestly. Even I've been doing C sharp since there's been a C sharp, and I bump into that, you know, still bump into that occasionally. So, you know, that's just life. That's just, you know, being a developer. So it's not a big deal. Um, but you just have to kind of stick with it and plow through it and do. Um, and the most important thing is this creating this mental model of this structure, because we want to get into the brains of the people who developed this and say, okay, what were you trying to do? How were you trying to lead me? And so then, you know, their goal is the memory safety, right? And so I have to look at everything through the lens of memory safety. How does this syntax, how does this approach make life better for me as somebody who's worried about memory safety? And as long as I can do that, and as long as things fit, then it's not going to be so bad. And we'll see. So anyway, I'm not going to kind of plow into traits at this point. I'm going to save that for next time. But anyway, so thanks for watching, and I will see you later.